Okay, in this presentation we are going to look at Project Euler question 10. And this is another one that is concerned with prime numbers. We are using Julia version 1.6.1 and we are using Jupyter Notebooks. And this set of presentations are aimed at people who are new to computing and new to programming, let's say undergraduate students of mathematics, statistics, engineering, and so on. So the question is, the sum of the primes below 10 is 2 plus 3 plus 5 plus 7. That is equal to 17. Now, just actually as a remark, it specifically says below 10. Just let's pay attention to that. And also, so anyway, find the sum of all of the primes below 2 million. Okay, so let's just get started here. So what we're going to do here is use a package called primes, capital P, using primes. And what we're going to do there is use a command there called primes, small p. And the input of this will give us all of the prime numbers less than or equal to that. Okay, so primes, let's just check that for 10. Okay, so it's a 4-element array there. So that, if we were to sum that up, that would give us 20, or give us 17. Okay. Now, correctly, what we should do here is it's below 10. Now, as it stands, this gives us all of the primes less than or equal to the input 10. So what I really should do there is change that to n minus 1, 10 minus 1. Let's just check that. Do I need another bracket there? Yeah, that's fine. Okay. Now, so the sum of the primes less than 2 million. Okay, so I'll just go 2 million minus 1 there. Okay. So that's less than or equal to 1,999,999. Okay. Essentially what we do there is just simply add them up. That seems very easy, doesn't it? Okay, well, there we go. So let's just look at this. We seem to have a very big number there. 1.429 trillion approximately. Okay, seemingly that was very easy. Now, the thing is, that's almost too easy, and we don't really learn anything by that. So what I'm going to do is actually rerun this approach, and what we're going to do there is see if we can learn a little bit more about it, because really the question there as posed lends itself to a very simple solution thanks to the primes package, primes, the function in the primes package. But let's actually just see if we can learn a bit more about this process in case we have to deal with other things and things won't be so easy. So what I'm going to do here is write a function there called sum primes of n, okay? And the sum, and by the way, I'm going to drop the below, so it's less than or equal to from now on, this function here. So we just put in n minus 1 if we want to be very particular about it. So function sum primes of n. So what we do here is set the sum equal to 0 and add them all up and then output the sum there. So that's straightforward enough. And that gives us what we need pretty much straight away. Okay, and that's the number again, the summation there again. And this actually also gives us a sense of the processing time there. 0.0043351. Okay, so that's the processing time. That's important actually. Just sort of keep an eye on that, because there's a sort of it's a sort of good to sort of develop this facility to compare the speed and complexity of various different algorithms. Okay, so that's that ellipsed there. Now, what is important here is the size of the integers we're dealing with. Okay, so let's get 2 to the power of 30. Okay, seems straightforward enough. Okay, that's a very big number there. Okay, it's a 10-digit number. I'm not going to 10 billion or something like that. Okay, 2 to the power of 32. Okay. Now, just actually as a remark, something I should note is that I'm working on a 64-bit machine. If you're working on a 32-bit machine, you're going to hit a problem here very quickly. I'm about to hit this problem here on a 64-bit machine. So if you're on a 32-bit machine, you just hit it on there previously. I'm about to hit it now. There we go, 0. So 2 to the power 64, is that equal to 0? That's not what my reckoning. What we have to do here is we're dealing with integers, but what we have to do here is if we're dealing with big numbers like this that need extra space, extra room, essentially what we have to do is use big int. This is a special type for dealing with large numbers. So essentially what I'm going to do there, it's an integer with just more space, data type with just more space allocated to it so that it can work with bigger numbers than usual. That's all it is really, okay? Big integers, just when things get big. We can have small integers stored as big integers, okay? Anyway, big int. Let's see if we can work with that now. There we go, big int. There we go, that's 2 to the power of 64. Really big number there. I'm not going to verbalize it, but there you go. So what I can do here is, if we're dealing with very large numbers, and that go beyond the size that we can store in memory as integers, we can just sort of set them up as big integers, big int. So I have some here stored as a big integer, okay, and essentially what I'm going to do is just add all the prime numbers up into that consecutively and then just store it. Okay, so let's just run that. Okay, there we go. So that's it stored again. Okay, now you notice it's a bit slower, 0.0675765. Okay, so there's a bit of a overhead, a cost incurred due to using big int, okay, as a data type. So it's straightforward enough, really. I mean, this sort of does the job, okay, but we don't. It's nice to know, for other variations where things might not be so simple, that we might have big int to rely upon, okay, if things are tougher than we think. Right, that's it. We'll leave that there.